let's look at a flow that comes up a couple of times in fluid mechanics in general and biofluids in particular. So let's say I have a flat plate, the ground or something like that. And then imagine I have some flow that kind of comes down, hits the surface, and sort of gets redirected to the sides. So what might some streamlines of this flow look like? Well, we might have some flow, in the very center. That flow comes down and is kind of brought to halt right there. We could also have flow that sort of comes down, and to the right of it, it sort of gets redirected over here, and to the left, it kind of gets redirected over here. Now, strictly speaking, we can't have flow directly, the flow immediately next to the wall is moving, but a lot of times if we as long as we're not too close to the wall, we might have some kind of thin boundary layer from the wall where, inside the boundary layer, we have this transition from no flow up to the flow here, but just outside the boundary layer is what we're interested in. So, flows like this, where we have some, jet or some stream that kind of comes in, hits a surface, and gets directed to the side. This happens all the time in biofluids. So, for example, one instance is where we have a jet for irrigating or cooling during surgery. So when I was an undergrad, I did some undergrad research in the mechanics of bone sawing, and bone is actually like a remarkably tough material. So when bone is getting sawed, the friction from ineffective bone sawing can actually heat up the bone so much that it boils the water out of the surface of the bone and kills the surrounding tissue. And this has problems later in terms of patient discomfort, but also a layer of dead bone can eventually get eaten away and cause implants to fail, right? So if you're like getting a knee replacement, they'll cut off parts of your existing bone knee and then put in the implant. That implant would fail if it's adhered to dead bone instead of living bone. So what they'll do is they'll saw for a little bit, and then they'll spray a jet to wash out all of the bone chips as well as cool the surrounding tissue. So if we're interested in saying, hey, is this, how is the flow happening? Is this flow going to be sufficient to carry away heat later? We might be interested in sort of describing, what are the shape of these streamlines? How fast is the fluid moving in a flow like this? If we touch back to an earlier part in the class and look at the system kind of upside down, we have some flow kind of coming up and hitting a platform in the bottom, and we could levitate some cats with that, right? So when we were doing conservation of momentum, we sort of said, we're just going to look at the system kind of in wholesale and look at ins and outs in terms of momentum to look at the force on the cats. But, maybe we want to zoom in and start investigating exactly what's going on here. So, cat levitation. Very serious bioengineering example right there. Finally, there's a third thing. If you've ever gone to the optometrist office, you'll have your eye, and they'll put you'll sort of sit your chin on this little machine, and then there's this little nozzle right here, and it shoots a puff of air at your eye, and it always makes me a little nervous. I'm looking at my eye, and then I jump a little bit, and when you're looking through, you might see like a hot air balloon in the distance or whatever. But basically what that puff of air is doing is it's deforming the outside of your eye just a little bit with some pressure, and the deformation of your eye can, based on the deformation of your eye, the machine infers what your interocular pressure is. And if your interocular pressure is off, then that can basically mean you could have like glaucoma or some really nasty disease. So if we look at what's happening, this little puff of air basically hits your eye and gets redirected to the sides, that's a flow pretty similar to what's going on here, right? So we could talk about interocular pressure measurement by this somewhat goofy or somewhat unpleasant but not totally invasive device here to measure your eye pressure and look for diseases. So there's this handful of examples where we might care about a flow like this. So let's work out an example problem where we'll be able to get information. We'll be able to get information about what the velocities look like in this flow, and we'll practice using continuity. So we'll investigate this flow, and we'll do so via the continuity equation, or as we called it in the previous lecture, fully micro conservation of mass. So that's the plan. So in general, conservation of mass types problems help us get information. If we have information about velocity, about some velocities in the flow, conservation of mass generally helps us get information about other velocities in the flow. So basically what conservation of mass does is it allows us to relate velocities in parts that are known to relate that to velocities in parts unknown. And this velocities in parts that are known to velocities in parts that are unknown. This is true whether you're talking about macro conservation of mass or shells or fully micro conservation of mass. And we're going to analyze this flow in terms of fully micro conservation of mass. So a lot of times when people are sort of investigating flows experimentally, sometimes it's easy to observe some velocities but not others. So let's look at the example here where I have some flow, some flow that's kind of streaming into a surface, and let's say instead of a solid plate here, let's say it's a clear window. And just below it, I have some camera. Some camera looking up at the bottom of the flow. And if you can imagine, if I'm a camera sitting here at the bottom of the flow, let's say I could put some origin y and x right here. If I have a camera looking at the flow, it's very hard for a camera to detect velocities, coming closer to you or going away from you, but it's pretty easy for cameras to detect side-to-side velocities, right? So you can imagine if I have this camera right here, what does this camera enable? This camera enables me to observe x velocities, but it would be really hard for that camera to sort of observe y velocities. So camera basically can observe x velocities, but it would be really hard to observe velocities. And well, if you're saying, hey, wait a second, is this just, if this is a fluid, how can a camera even see velocity in a fluid? Well, there's this technique called particle image velocimetry. So particle image velocimetry, where they basically take a whole bunch of tiny little particles and suspend those particles in the fluid, and then have a camera capture video of those particles moving along. And by doing sort of particle tracking and image analysis, you can basically say, hey, the particle was here in one frame, and then it was here in the next frame, so the local velocity must be in that direction. So we can basically put in a bunch of little tiny particles that don't really affect the flow in any way, but just the particles sort of are carried along, and then we can image those particles with a camera. So if we do this, it'd be pretty easy to detect how particles are moving in the horizontal direction. Again, that's sort of like me moving my hand with respect to this camera here, but it's a little bit hard for the camera to detect particles getting closer or farther away via this technique. So what does that look like? Let's say we're given, so let's frame this a little bit more mathematically, right? So let's say we're given information about the x velocities via our camera. And let's say we've experimentally determined that our x velocity is given by the following function. Some constant, I'll just call it beta, times x. Right, so from my image analysis, I determined that a function that describes the x velocity of kind of any of these particles in the flow is given this, is sort of described here. So what does this mean? Basically, this is kind of consistent with what I've sketched here, where the particles along the center line at x equals 0 don't have any x velocity, but as the particle, for streamlines that are farther away from this kind of center streamline, the particles do indeed have more x velocity, right? So, the particles here are moving much faster than the particles right here. And that's kind of consistent with this sort of stagnation region under here. So let's say we're given this information about x, and let's say we want from our information in x, do we have enough information to, for example, figure out what the y velocities are, right? So let's say we're given information about x, but let's say we want vy, and not just vy at any particular point in the flow, but we want a whole function to basically describe what the y velocities of any particle in this flow is. And let's sort of assume we're just dealing with a 2D system here. That if I go to any other point, let's say in the z-axis, the flow is the same sort of at any z slice that I check, right? So let's say we're given this vx, and we also know that vz equals 0, and that there's no z variation in the flow, right? So let's say we're given this information, and we want to determine a whole function for v of y at any point in the flow. Is it possible to do this? Yes, via continuity and fully micro. So let's get started. So, regardless of whether we're talking about water for a jet irrigation problem, or water for cat levitation, or even air pressing against someone's eye, as long as we're dealing with flows that aren't approaching the speed of sound, it's a pretty solid assumption. Right, so I guess let's pull these into our assumptions here, but it's also a pretty good assumption to assume that we have a constant density, right? That the fluid is incompressible, and as long as we're not sort of like dissolving things in this water as we're going along, or heating it up too much, it's a pretty solid assumption to assume that that density is a constant. So we have information about one velocity. We want information about another velocity, so that prompts us to think about conservation of mass. We're looking to essentially derive velocity profiles in a sense. So in that sense, we're going to, shells might come to mind, but also this continuity or fully micro version might come to mind as well. So if you're looking to derive whole functions, something like this, if you're looking to relate velocities, some known velocities to other unknown velocities, conservation of mass is going to be your workhorse there. So let's proceed with this. So if we assume our v equals 0 and no z variation, as well as density is equal to a constant, we can use continuity, and we can use the simpler version of continuity, which is dvx dx plus dvy dy plus dvz dz is equal to 0. So here we have continuity. Right off the bat, we can make some simplifications to continuity. We basically said, hey, we're assuming that flow is only really moving in x and y. We don't have flow into or out of the page. And we also are assuming that we don't have z variation as well. So either of these assumptions would enable us to get rid of this, right? If vz equals 0, then its derivative is also 0. If we have no z variation, the derivative of anything with respect to z is going to be 0. So for both of these things, we can basically get rid of this third term here. And now we're left with basically two partial derivatives, dvx with respect to x and dvy with respect to y. So let's kind of plug in these things right here and see what progress we can make. So what do we have here? So we can plug this in. So we have now partial with respect to x of this constant beta times x. We just plugged in our Vx into here, and we're going to plug our Vy into here. So, Vy was some unknown function, so when we plug it in here, we kind of need to treat its derivative with respect to y also as something kind of unknown, yet to be determined. So those are equal to 0. Or the sum of those is equal to 0. So we can actually take this partial derivative, right? I can take a partial derivative of some constant times x. So the partial derivative of this constant times x, well, that's just the constant itself, right? So what does this mean? I now basically have beta plus this derivative of Vy with respect to y is equal to 0. All right, can I make progress with this? Well, this is a partial differential equation where we have a partial derivative of Vy with respect to y plus a constant is equal to 0. Well, perhaps I can go about trying to solve this differential equation. Right? So I can take this differential equation, I can move minus beta over to the other side, and what am I left with? Well, I have dvy dy is equal to minus beta. I can multiply each sides by dy and integrate. And if I integrate the left-hand side, remember if I integrate partial Vy dy, then I get Vy on the left-hand side. And then if I integrate the right-hand side dy, I basically get minus beta times y. So pause and ponder. Am I missing anything right here? What am I missing right here? Well, some of you might say, hey, if I have these indefinite integrals, do I get a plus c? And under some circumstances you would, but remember when we're integrating partial derivatives, it's not plus c, but rather plus some function of any other variable except for y, which is here, right? So in this case, it's plus a function of could be x, not y, but could be z or t as well. So if we're talking about partial derivatives here, right, if I took the partial derivative of both of these of each of these sides with respect to y, I would end up back at this equation here, right? If I took the partial derivative here, then I'd have this. If I took the partial derivative of this with respect to y, I'd end up with beta, which I could bring back to the side. And if I took the partial derivative of a function of x, z, and t, if I took the partial derivative of this with respect to y treats all of this like a constant. So this whole thing disappears if I took the partial derivative, right? So that's why it's not plus a constant, but plus a function of all of the other variables when you integrate partial derivatives. So here I am left with this function that's yet to be determined. So let's see if we can make some progress with this function here. So we already assumed in our set of assumptions that we had no z variation. So if we have no variation in z, this function can't depend on z as well, right? So basically, if we have no z variation, then this function can't depend on z. So now we basically are looking for this thing of f as a function of time. I think we might need to go back to our assumptions here, and if we additionally assume that the flow is steady, which I guess was true for the cat levitation problem, would be pretty much true for the jet irrigation, is a little bit of a stretch for the interocular pressure measurement, right? Because they're sort of sending a puff that's like by its nature kind of transient, but bear with me. So if we assume steady, then we can get rid of the t dependence of this function as well. So what does this mean? We now have Vy is equal to minus beta times y plus some as of yet unknown function of x. So take a moment now, pause and ponder. How can I figure out what this function is, right? How do I get information about this function of x, right? How do I resolve what this f of x is? How do I resolve that? Well, if you're thinking the same way I am, when we get constants of integration, we typically resolve them with boundary conditions, or in this case, when we get functions of integrations, we can also resolve them via boundary conditions. So what am I talking about boundary conditions? Well, boundary conditions are essentially parts of the flow where we know information about. So take a moment now, pause and ponder, are there any boundary conditions about this flow that will help us resolve what this function is, right? So what boundary conditions, pause and ponder, what boundary conditions might be present to help us resolve f of x? Well, if you're thinking the same way I am, if I'm thinking about this flat plate, I have the most information about this flat plate here. And I'm thinking about this flat plate. The flat plate basically redirects the flow. I can't have flow that enters this solid, that cuts into, that jumps into this solid material, right? Solids don't have fluids just going through them. So what does this mean? So how do I translate this into a boundary condition mathematically? Well, if I basically can't have flow that's entering into this plate at y equals 0, Vy must equal 0 as well. So that's basically saying at the flat plate, the y velocity has to be 0 where I don't have flow that's kind of entering into the plate. So what does this mean? I can basically take this boundary condition and sub it into this equation right here. So Vy equals 0, my left-hand side is 0. When I sub in y equals 0, this first term is 0, plus f of x. Well, what does this mean? We basically conclude that f of x is equal to 0 from our boundary condition, right? So our boundary condition basically gives us all of the information we need to resolve f of x. So what does that mean? Well, we now have basically fully resolved Vy in terms of stuff that was given to us. So now Vy is basically equal to minus beta y. Great. So when we get to a point like this, it's probably good to do a few sanity checks. So one of the first sanity checks is, is this consistent with what we've sketched for the flow? Is this equation consistent with what we've sketched for the flow right here? Well, if I think about it, Vy for positive y, this quantity is negative, right? So basically saying if y is positive, the minus sign out front, and beta being a positive constant basically means that Vy is negative. And that's consistent with the flow going down, right? If I'm above the plate, the flow is going down towards the plate, so Vy is negative. This makes sense. This is also saying that if I start up, far away from the plate, this flow is pretty fast. But as I get close to the plate, y is getting smaller and smaller and smaller, so Vy is getting smaller and smaller and smaller. So it's basically saying, hey, out here the flow is moving pretty fast, but as this flow gets closer and closer and closer to this plate, the flow gets slower and slower and slower, or at least the y component of the flow gets slower and slower and slower. And that's basically with particles kind of fluid kind of screaming towards the plate, slowing down, and then getting kind of redirected as they get shot outwards towards the side. And that's kind of consistent with what I've sketched right here. So qualitatively, this at least matches in terms of like the directions of flow, and flow being up or down and left and right in terms of positive and negative y. So this definitely passes that test. Another test we might want to consider doing is units. But in order to figure out the units, we basically need to think about what units this thing beta has. Well, if I compare, beta here was basically given in this part of the problem right here. So how do we figure out the units for beta? Well, Vx has to have units of meters per second. X has units of meters, so that means beta has to have units of 1/seconds. And then if I plug that in here, it's basically the same story here. Vy has to have units of meters per second, y has units of meters, and beta still has units of 1/seconds. So the units check out as well. So So how is this useful? We've now basically we were given only information about the x and z velocities, and through continuity we were able to relate the velocity of parts that were known, i.e. our vx and vz, to velocities that were unknown, for example our y velocities. And this might be important for saying, hey, what is the nature of this flow? How is, for example, this flow applying pressure to the outside of the eye, or how are the velocities of this flow carrying away chips or cooling down the surface of freshly sawed bone, for ultimately improving patient health. So hopefully you found this example problem useful. Thanks for watching, and good luck with your study of fluid mechanics.